All right, let's talk about a concept that sounds super sciencey, but is actually something you already get on a gut level. It's called half-life, and it's a huge deal in physics, chemistry, even archaeology. I promise, by the end of this, you're going to see it's a pattern you see all the time. So let's crack this code. Seriously, picture it. You sit down with a giant tub of popcorn. The trailers start, you look down, whoa, half of it's already gone. The movie gets going, you look down again, and you've eaten half of what was left. It's this repeating pattern, right? A predictable way things just disappear. Okay, fair question. What on earth does movie popcorn have to do with radioactive atoms? Well, here's the cool part. That simple, intuitive pattern of your popcorn vanishing is the exact same principle that runs some of the most powerful processes in the entire universe.
So we're going to call this the popcorn principle. It's the simple idea that in a set amount of time, a chunk of something will decrease by half. Let's really look at what this means.
See the pattern here? It's all about consistency. In those first 15 minutes, half the tub is gone. But in the next 15 minutes, you don't finish it off. Nope. You eat half of the remaining half, leaving you with a quarter of a tub. Another 15 minutes go by, and you eat half of that, leaving an eighth. Each time, it's always half of whatever you had left. And there it is. That's the big reveal. That exact same pattern is what scientists call half-life. Except, of course, they're not talking about popcorn. They're talking about something way more fundamental. Unstable atoms that are literally breaking down or decaying all on their own predictable schedule. So, let's step out of the movie theater now and take this idea down to the atomic level. This is where things get really, really interesting. So, the most important thing to get here is that half-life is all about time. It's the specific amount of time it takes for exactly half of a pile of radioactive atoms to change into something else. Not all of it, just half. This is exactly what it looks like with atoms. You start with your initial amount, we'll just call it N0 for now. After one half-life passes, bam, you've got half of it left. After a second half-life, you've got half of that, which is a quarter of what you started with. You see, it's what we call an exponential decay. The amount doesn't drop in a straight line, it drops by a percentage of whatever's left, making a curve that gets flatter and flatter over time. Now here's a super useful way to think about this. You can talk about how much stuff is left, or you can talk about how much stuff is gone or has decayed. They're just two sides of the same coin. They have to add up to 100%. So if 25% is left, you know for a fact that 75% is gone. The math for the fraction that's left is super simple too. It's just 1/2 to the power of n, where n is just the number of half-lives that have passed. Okay, so how do we actually use this stuff? Well, when you're faced with a half-life problem, there are basically two great ways to figure it out. One way is just pure intuition, and the other is a really simple but powerful little formula. Let's try a real-world problem. Say we've got 200 grams of iodine-131, a substance used in medicine. We know its half-life is exactly 8 days, so how much is going to be left after 32 days have gone by? Let's try the easy way first. You can literally just map this out. No fancy calculator needed. We start with 200 grams. After the first 8 days, that's one half-life, we cut it in half. 100 grams left. After another 8 days, we're at 16 days total. Cut it in half again, 50 grams. We just keep doing that until we hit our target of 32 days, which gets us to exactly 12.5 grams. See? Simple. But, what if the numbers are messy? What if it's 27 days instead of 32? That's where the formula is your best friend. Here, n is the final amount you want to find. N0 is your starting amount, and that little n is just the number of half-lives. So let's just plug in our numbers. Our starting amount, N0, is 200 grams. To find n, the number of half-lives, we just divide the total time, 32 days, by the length of one half-life, 8 days. 32 divided by 8 is 4. Perfect. So our equation is 200 times 1/2 to the power 4. You punch that in, and what do you get? 12.5 grams. Look at that. Two totally different paths, but they lead to the exact same place. Okay, so you might be thinking this is just a neat math trick, but it is so much more than that. Understanding half-life has literally allowed us to unlock the secrets of the ancient past and build some incredible modern technologies. And I mean, this is stuff we use every single day. Carbon dating? That lets us look thousands of years into the past just by measuring how much carbon-14 is left in a fossil. In hospitals, that steady, predictable radiation from cobalt-60 is used to sterilize equipment and bandages, which saves countless lives. And when doctors need to see what's happening inside our bodies, they use special tracers with really short half-lives. that light things up for a bit and then safely fade away to nothing. It's amazing.
Just look at that number, 5,730 years. That is the half-life of carbon-14. It's this incredibly long but incredibly reliable clock that lets archaeologists date a bone or a piece of wood with amazing accuracy. They know that after 5,730 years, exactly half of the carbon-14 that was in that living thing will be gone. It's like a cosmic stopwatch that's been ticking for millennia.
So for a big sample, we're talking billions and billions of atoms. Half-life is rock solid. It's predictable. We know with almost total certainty what's going to happen. But what if we zoom all the way in? What happens when you're down to just one single atom? All of a sudden, that certainty just vanishes. For that one single atom, the next half-life isn't a guarantee of anything. It's a coin flip, a 50-50 chance. It might decay, or it might just sit there. And that question, what governs that final coin flip? That takes us out of the world of predictable physics and drops us right into the strange, mind-bending world of quantum mechanics. It's a pretty profound thought, isn't it? That at the very heart of our universe, it all comes down to a roll of the dice.